All right, so video 2 on severe thunderstorms, focusing on types and behavior of severe thunderstorms. So, we can categorize thunderstorms into 4 general types: single cell or pulse systems, multi-cell clusters, multi-cell lines, and supercells. Severe is a categorization sort of separate from those 4 different structural classifications or structural organization types. Severe means that it meets or exceeds severe thresholds. So in the US, we talk about these are our severe thresholds: greater than or equal to 1-inch hail, greater than or equal to 58-mile-per-hour wind, or existence of a tornado with the thunderstorm. So here we'll be going over the 4 categories, actually talking about the impacts of the phenomena associated with it. That'll be the next video. And tornado is actually next week. So, first kind, pulse. Also, you may hear it referred to as an air mass thunderstorm, or a single cell, or an ordinary thunderstorm, sometimes even garden variety thunderstorm. These are often triggered by warm bubbles, surface heating, and they don't last very long, typically on the scale of half hour to an hour. And the reason they don't last real long is because there's weak to no wind shear. So that, as seen in this little diagram over here, you get an updraft from your initial warm bubble, you get your moist convection going up, but as soon as you start getting precipitation, that forms cooling, which then is dense air that sinks. You get a downdraft. That downdraft, because there's no shear, has nowhere to go. It just falls right back where it came from, on top of the updraft, which, once enough of that precipitation forms, ends up causing the system to dissipate almost right away, and it becomes outflow dominant, or downdraft, over the updraft, and it dies out. These are rarely severe. They just don't have enough time to develop enough of the dynamics needed to produce severe weather phenomena. At the very most, if you have an extremely strong warm bubble and the right environmental profile, you can maybe get enough of a downdraft to have some severe winds, but these are very rarely severe. And as shown here, it's sort of 3 stages. Cumulus stage, where it's just the updraft, no precipitation yet. That's initial formation. Mature stage, where you're starting to get precipitation, but you still have enough of an updraft to keep the system growing. And then dissipation stage, where your updraft is dying out, or almost completely died, or has died out, and you're just getting the remaining downdraft, the remaining falling out of precipitation and cool air. Moving on to multi-cell clusters, it sort of builds off of pulse storms, where now you have a group of cells that are all clustered together, and they move and behave really as a single unit. But each of these component cells of the cluster, they're each at a different stage of that single cell life cycle, and sort of in an order as you progress through space in the cluster. Sort of as shown in this diagram here, where you have cumulus stage developing off on one end, cells in the mature stage in the middle, and dissipating on the end. And these, in order to get this kind of organization and clustering, you do need to have some shear. You don't need as much shear as the following types have, but the other thing is that these are generally more weakly organized. They don't often need or have to have some kind of organizing boundary to develop on. They can just have enough shear that this can organize, and you end up getting continual development. And this can produce severe weather of all kinds. Not that often tornadoes, because you aren't getting mesocyclones that are really supportive of that, as we'll talk about in the supercell section in this video, and tornadoes next week. But it can produce severe weather of all kinds. It's not, though, as likely as the remaining 2 more intense, more strong, well-organized types. That brings us to multi-cell lines or squall lines. And these are continuous or semi-continuous lines of convection. Sometimes you can see the component cells along the line. Sometimes they're all just blurred together into a single linear connected segment. And these need strong speed shear and some kind of organizing boundary in order to develop this structure where you have leading updraft going into the storm, downdraft coming out behind. But I say it needs an organizing boundary. Sometimes these self-develop, and their boundary that they organize along is their very own outflow boundary. The other times is that they can organize a cold front are also conducive for organizing these types of systems and providing the shear needed. And these can also produce severe weather of all kinds, but it's particularly notable that we have straight line winds, very intense winds, and severe and damage producing winds for forward propagating systems that are moving along, that you'll typically see in a system like this. The other thing I mentioned, cold front or outflow boundary can also organize along warm fronts and stationary boundaries, but in sort of the opposite direction. Instead of propagating forward, it can actually move sort of along the boundary, where you end up getting convection over the same region for a long period of time when in a training fashion where you just get cells popping up over and over again, or back building where it's always building off of itself. These kinds where you get convection over the same area for a long period of time leads to a lot of types of flooding. And here we actually can go in and talk about some particular subtypes that you might hear mentioned. Bow echo is a particularly multi-cell line that has a strong enough rear inflow jet, so the air coming into the system from behind it causes the convection to bow out, and that creates that bow-like signature on radar, hence why it's called a bow echo. And these are particularly associated with severe wind compared to just any other linear system. Bow echoes have a particularly strong threat of severe wind. Going all the way up on severe wind threat, we have derechos. And bow echoes, if they're particularly severe, can be derechos. But derechos refer to when we have a particularly damaging linear system like this, but it can really only be assessed after the fact. Bow echoes, you can tell based on radar while it's happening. Derecho can only really be assessed after it's done enough damage, and the criteria typically used is for a derecho, you have to have wind damage of more than 240 miles with gusts of at least severe criteria, 58 miles an hour along most of that length. So an extensive, wide, long wind damage swath gets you a derecho. And typically when you have one of these advancing linear systems, see a very classic cloud pattern called a shelf cloud. And this is where you're seeing that inflow air being brought up into the storm system. It condenses in a nice laminar fashion. You get this long, broad, smooth cloud, and then all of your outrushing cold air coming along it. So this cloud really outlines that outflow boundary of the system that is both being produced by the system as it's continually precipitating and forming that outflow, but it's also the outflow boundary on which the system's updraft is organizing and providing that continual lift mechanism in a sort of self-reinforcement or a feedback mechanism that continues to maintain the system's strength. So supercells, our last type and probably the one that there's the most to talk about with. Supercells really are, derechos can be particularly intense, so some supercells are weaker than some linear systems. But in general, supercells are your most intense thunderstorms. And the key thing that defines or differentiates a supercell is that it possesses a mesocyclone, which is a rotating updraft that creates enough system dynamics that allow supercells to be much larger and to persist for a lot longer time on their own than just your smaller pulse thunderstorms. These require speed and rotational shear and at least moderate cape in order to have that updraft and downdraft separation, enough rotational shear and speed shear being tilted by the updraft in order to cause the updraft to rotate, and cape to get a strong enough updraft to maintain these kinds of larger cellular systems. And they can really be triggered by any mechanism, but most often, just because of the surrounding dynamics to support them, most often you'll see these along warm fronts or dry lines, just where all the shear and all your ingredients come together in the best way possible for supercell development. And these are typically the most prolific producers of severe weather. Every single severe weather threat can occur with these, and compared to the other types, they're particularly known for their large hail threats and tornadoes. Most of your tornadoes are going to come that are of higher damage are going to come from supercells. Sometimes, we may talk about briefly in the tornado sections, you can get tornadoes from supercells embedded within linear systems. But that's a little bit more complicated, and we won't touch on that right now. So, looking at the picture of a supercell, this is sort of an idealized view of a supercell. It's cumulonimbus, a thunderstorm cloud, and it's going to have a flanking line on one side where you have sort of that gust front, some of the air wrapping around that rotating mesocyclone coming out and leading into new development that feeds into the main system. Because of how intense it is, there's an overshooting top where you get so much updraft strength that it goes beyond sort of the equilibrium layer where otherwise you're going to balance out, and that's also the level where your anvil spreads out because you're sending all of this moist condensed air out, so it just sort of spreads out and forms your anvil. The overshooting top, because of the updraft strength, goes beyond that. You get your large broad regions of precipitation. Rain is going to happen with this most of the time. Hail also can develop. That we'll talk about next video about how hail forms. That's with the interaction of the updraft and downdraft. And also near the base of the updraft, that's where you can get your wall cloud and tornado coming out of this, where you get your storm scale mesocyclone dynamically supporting lower level rotation until you get enough vorticity that stretches together till you get tightening and you can get a tornado to form, which is a rapidly rotating column of air, contact with the cloud base and the ground. Looking at another schematic view, these are somewhat complicated diagrams. You don't have to know every detail, but I'll just sort of use them to describe a couple things. In your typical supercell layout, you have sort of two downdraft or two outflow regions. The forward flank, your main regions where most of your rain is going to come out and air is going to sink because it's cooled and travels with the rain. But you also are going to have, because of the rotating updraft, there's enough strength to pull some of this around the other side towards what we call the rear flank. We call this the rear flank downdraft region. And so that's how you see these colored regions here. That's about what you see on radar for one of these systems. And you get the classic signature known as a hook echo, where you have this hooked region of precipitation going around the mesocyclone. So the key thing that causes a hook echo signature, your classic supercell signature on radar, is that you have precipitation wrapping around the mesocyclone into the rear flank downdraft region. And where that downdraft air from either the forward flank or rear flank downdraft, where that meets the inflow air, the warm, moist air coming in, we have what's called a gust front. This is also an outflow boundary, but in this particular context, it's also referred to as a gust front. And a lot of the interesting stuff in a supercell happens right where the mesocyclone is and where these two different components of gust fronts happen. This is typically where your tornado would form if a tornado forms with the supercell, and it's right below where your mesocyclone goes up, and your mesocyclone is where you get hail formation, and it's where your winds wrap around to form these downdraft regions, which is how you can get really dense cooled air that sinks to the surface, and you can get your severe wind out of these systems. So a lot of interesting dynamics going on in supercell that all act to mutually reinforce each other and contribute to the severe weather that supercells can produce. Supercells have 3 subtypes based on their precipitation extent, how intense or broad their precipitation is relative to the updraft characteristics. Talked about the one that was really focused and shown in the previous slide was the classic supercell. And that's where you have a balanced region of precipitation with your updraft core. You're going to get some wraparound in your rear flank downdraft, but enough that you have pretty clear slot also for your inflow air to come up, and you'd have a pretty clear view of any wall cloud or tornado that would form near the intersection of your updraft and downdraft regions. You also get low precipitation, where you get enough upper level wind and just less intense, less moisture, that your precipitation is more further removed from your updraft region. And so you get really broad, clear views of what's happening in your storm. These are usually really picturesque and ones that your storm chasers like to see a lot because you can see things really clearly on what's going on in the system. They can also be associated with hail threats. High precipitation sort of flips that in the other direction. Instead of getting just precipitation that's farther removed from the updraft, here you get precipitation that is in a lot denser bands and sometimes surrounds almost the entire updraft region. And so any sort of wall cloud or tornado can be rain wrapped. It can be hidden behind precipitation regions. And this is the kind of systems we tend to get here in Iowa. And a lot of storm chasers don't like that because, one, you can't see as much. It's not as picturesque. And two, these are rather dangerous. When a tornado happens and you can't see it coming, it's a really dangerous situation that either as a member of the general public or as a researcher or as a storm chaser or a storm spotter, you don't want to be in. You want to have good situational awareness to be able to see what's going on. So these are ones where you want to shelter and be very, very careful around. And so that brings us to the end of these supercell subtypes. And again, talked about in this video, those kind of things like hail, severe wind, tornadoes, those get into our actual impacts and threats. And that's what we'll be focusing on in the final video of this severe thunderstorm section coming up next.